through it.
No worries. So we know technology can be tricky at times, but thank you for helping us today. Um, and then with that, I will let you take over and just let me know when you want me to switch slides.
All right, that sounds good. Yeah, so this is the build and assembly webinar. Kind of self-explanatory as it is. I'm Adrian. There's no introduction slide on the next slide, so I'll just go over it now. I was yeah, I competed in a variety of competitions throughout my time working in both high school and college. I didn't do First Nations launch, but I did the kind of sister competition that launches at the same time, which is the Collegiate Rocket Launch sponsored by Wisconsin Space Grant as well as a couple other competitions throughout my time. I graduated from college in let's see 2018, and I've been working since then as a mechanical design engineer at a company that is now called Coperion Process Solutions that does food processing stuff. So not aerospace. There actually have been some of our machines. Turns out the machines that feed sugar work just as well to feed other powders that might have aerospace applications. But most of it's food processing stuff that I work on. So that's a little bit about me and where I'm at. I've been building rockets for, better part of 15 years. I have my level 3 certification. I've been flying, high power level 3 projects for about 5 years or so now. So that's me. Hi. Next slide, please. All right, so we're going over the kind of general overview of, how to build every step of a rocket. So you've probably seen this before. I know in past years this diagram has been on previous presentations. It just kind of covers the overview of the parts of a dual deployment rocket. You have, the aft part with the fins, the motor mount, the drogue parachute. You have this avionics bay coupler in the middle, and then off on the top you have the nose cone and the main parachute right below it. So most of the assembly will be concentrated down gluing the fins and motor mount and everything assembly together, but we'll go through that as we go to the next slide. So this is basically the same thing as that previous slide, but here is showing on the top is a computer model cut in half, and on the bottom is an actual rocket that Dr. Flatten up in Minnesota was insane enough to cut in half. So you can see the exact same architecture where you've got, the nose cone, parachute, avionics, drogue parachute, and then the fin can section with the fins, the motor mount, the motor, all that centering rings, etc. That down at the aft of the rocket. Next slide, please. So most of the work going into constructing your rocket will be using adhesives of some description. Um, Generally speaking, that will be epoxy, but not always. And it's important to choose the right adhesive for the right job. You can look up, what material you're trying to glue to, and look at your adhesive, and it says this is good for, wood and metal, but not for plastic. And then use it for wood and metal and not for plastic. That sort of thing. You'll have to check in. Epoxy is a very good general purpose adhesive. It works for a lot of different things. But you can also use, CA glue or wood glue, depending. Wood glue works really, really well for wood and cardboard, but not so much for plastics or metal or that kind of thing. Um, there's also the difference between structural and laminating epoxy. Both of them are a two-part epoxy that you'll have to mix together to get, them to cure fully. But the difference is the viscosity. So laminating epoxy is more like, water or something very thin. It can be anywhere between, water and like maybe honey as the thickest it would possibly get, but somewhere in between there. And it's meant for wetting out like cloth fibers to do like a composite layup with fiberglass or carbon fiber cloth. Whereas structural epoxy has fillers pre-added to it from the factory, which allows it to form, more of a 3D profile instead of just, conforming to the bottom of whatever cup you put it in or so. So you can use that to form like a structural fillet in between two different surfaces. You can kind of fill in and smooth out the transition there. And that allows you to get much more contact area and a much stronger joint than if you were using a thinner epoxy. With all adhesives in general, going to the second bullet point here, more important than the exact adhesive that you select, if you choose, cheap 5-minute epoxy from the dollar store, or you go to 3M and you say, I want to spend $1 million on epoxy, give me the best epoxy you got, regardless of any of those extremes, generally speaking, you're going to be more limited by your bond prep than you are by the actual epoxy strength itself. If you do poor bond prep and you buy $1 million epoxy, it's going to perform worse than the 5-minute epoxy that you bought for $1 that you did good bond prep with. So very, very important to do bond prep. It's really simple, but you have to do it. So it's, you remove, some cardboards come with a glassine, a shiny outer layer. So that has to be removed. You have to peel it off or sand it off. Obviously, get any like grease or oil that you might have on the surface, wipe that down with an IPA alcohol or so. And then just do a little bit of light sanding to kind of scuff up the surface. This both it makes it mechanically a bit rougher and actually activates the surface chemically, which is a whole rabbit hole to go into, which I'll skip over that. But there's more information. I have some links later in the show that'll cover that. And then lastly, clean off all that sanding dust. And then you're good to go for whatever you're bonding to, whether it's metal, whether it's wood and cardboard, whether it's fiberglass. That's the basic steps in general. All right, next slide, please. So as we said, the vast majority of the gluing you're going to be doing is going to be on the fin can here. Is there? Yeah, there's more details in the PowerPoint later, so I'm just going to skip over this slide for now. We'll come back to these topics later. So next slide, please. Oh, I missed it. That's okay. Another bigger step is cutting out the flat components. If you're working with a kit, the kit manufacturer will have to do this, will have done this for you. But if you're scratch building a rocket, you will have to cut, fins and centering rings or the kind of flat components yourself. You can do this in a variety of different ways, and for me, it really depends what the material is as far as how I cut it and what tools I have access to. So on the right, you can see I used to have when I was in college, I used to have access to a laser cutter, and I really miss that. But laser cutters are wonderful for cutting wood. If you have one, I would recommend using it. Otherwise, on the left, there's a set of fins that I cut these out with a bandsaw. Depending on your shop supervisor, they might not like you using the bandsaw, so you might have to buy your own jigsaw and go do that out in the parking lot. However you want to do it, cutting clad components is relatively straightforward. If you have no tools at all right now, I would recommend picking up a jigsaw. It's kind of a cheap barrier to entry. It doesn't cost a whole ton, but you can cut basically anything with it. The caveat I would give is that it's very messy and very rough, so you got to be sure to wear your PPE, not only like safety glasses and keep your fingers well clear of the blade, but also you got to wear a mask because the dust, depending on what you're cutting through, wood dust is not great for you, but carbon fiber and fiberglass dust are way, way worse. So make sure you're wearing a respirator if you're cutting any composites with it. Um, and I would recommend marking it out carefully, cutting well outside of that, and then sanding to that line if you want the best possible fit. So that's a bit on cutting flat components like fins and centering rings and stuff. Next slide, please. Um, the other thing you will have to cut if you're built a kit, if you're working on like a kit for a certification rocket or what have you, the manufacturer will have cut these for you. But if you're scratch building a rocket, you will have to cut the slots in your airframe for the fins yourself. So the fins for a strong high power rocket, you want the fins to go not just mount to the surface of the airframe, but actually go through the airframe and glue to the motor mount. So I have a rocket here, actually. Let's see if this will work on the camera. That doesn't have a rear centering ring. So you can see, I'm not sure how well you can see that, but you can see their fins are glued directly to the motor mount in there. There's a bit of the fin that goes down through the airframe and touches the motor mount down there. So that's what we're doing here by cutting the fin slots. So here I have an example of my process for cutting fin slots in fiberglass tubes, and it's essentially the same process for any other material. The difference is for cardboard, I use a knife, whereas for any other material, I use a Dremel rotary tool, and you can see that in my hand on the left side there. On the right side, I have my preferred method of marking out. I use a bit of extruded angled aluminum, like 1 inch by 1 inch or inch and a half by inch and a half. And if you lay that on the tube, that'll guaranteed be a perfectly straight line up and down the tube. So I use that to mark out the fin slots where I'm going to cut with the Dremel. You can also, the old Estes kits recommend using a door frame for this, kind of the angle built into the door frame, kind of the same principle. I find that a bit awkward to kind of line it up and trace it out. So I like the angle, but both will work fine. Next slide, please. So here we have that motor mount assembly. So while you're gluing it together, this will be your first step is to glue your centering rings to your motor mount assembly. So again, just do bond prep as we talked about previously. The important thing here is that you have enough room for your fins tabs, the part that goes inside of the airframe, to stick in between your centering rings. So on the left, you can see there's plenty of room. That's not a concern at all. But on the right, you can see I have 3 different centering rings there. So I got to make sure that in between the bottom one and the middle one, that there is room for that fin to go in. And I had alignment guides built into the centering rings on this. So what I did when I tacked them in place I tacked with a bit of super glue first before I went and put the main epoxy on. And I had the fins in place while I did that to make sure there was enough room for them. So that's a tip is to, dry fit before you glue it and make sure you have that room. All right, Rob, next slide, please here. So here's two different methods of doing those internal fillets to glue the fin tabs to the motor mount. On the left is kind of the traditional high power method where you would leave that aftmost centering ring off and you stick in there with a long dowel and you pull your fillet that way, just pour in the epoxy and form a fillet. And that does work great, but is a bit awkward, especially when the motor mount is a significant portion of your airframe diameter. On the left is an 1.5 inch motor mount or 38 in a 4 inch tube, and you can see there's plenty of room to work. But on the right, we have a same size motor mount, but in a 2 inch tube this time, and there's not as much room to work. So what I did here is I just constructed all the fins and glued them to the motor mount outside of the fins, or sorry, outside of the airframe before I put them in. So that does allow you to do it. You have a much better control over getting the epoxy in the right spot. But the downside is you need to cut the centering ring, or the centering ring, sorry, the fin slots all the way to the back so you can slide it in. This isn't a huge deal because you'll do your external fillets and those will glue those sections of your airframe down in place very solidly. But it is a bit of a structural hit and probably more importantly an aesthetic hit if you don't want that aesthetics. The only time I personally would worry about the strength of that aft section of the airframe is on a two-stage rocket when you're using that as your interstage coupler, which I don't think anyone is this year, so that shouldn't be a concern. Next slide, please, here, Rob. So here's how to do external fillets that when aesthetics are a bit more important. You can actually go back to the previous slide real quick here, Rob. You can see on the right there, I didn't put a lot of effort into the aesthetics of my internal fillets on the right. So when you're doing external fillets, you might care a bit more about the aesthetics. So we'll go to the next slide. And here you can see the big advice that I have is to put masking tape literally everywhere that you don't want that epoxy to go because you'll get a little bit on your finger and then you'll try to go rotate it and you'll get a smudge of epoxy on it. And I've seen a lot of rockets that have beautiful fillets and then right by the fillets there's they put masking tape down, they're clean, but then on the fin or up on the body tube is a big handprint of epoxy because they didn't think they need to put the masking tape all the way up there. So that's my advice is put masking tape everywhere you possibly want. As far as the actual process goes, this is a thing I borrowed from Braden of Rocket Vlogs, if you know that YouTube channel, where he just rubs Sharpie on the end of a popsicle stick and then he uses that and he drags it along the fin. So you can see in the background there's just like a line drawn perfectly along the fin. So that's the popsicle stick is the tool that we're going to use to shape that fillet. And we're also going to use it to mark out exactly where that fillet is. So that if you have that line, you can just put the tape right along that line and you'll be good to go. So you can see on the third picture over, it looks really messy after I strike those fillets. There's all epoxy dribbled everywhere. But on the fourth picture, you take the tape off and it's perfect. So that's the secret. Next slide, please, Rob. As far as other methods or other areas you need to put in some construction, here's how I do my avionics bays. These are three different examples. The two on the left are very similar. They're all very similar. But the two on the left are the standard central avionics bay that we talked about earlier, where there's a section of coupler. Your avionics are mounted to the sled in the middle. You can see in the middle picture, I have a Stratologger, which is one of my preferred flight computers. Unfortunately, you can't get them as easily these days. But that's what I use. And then I have a screw switch to turn it on with, and then I have the battery, and I use just a 2S LiPo battery for that. So all of that is mounted to a 3D printed sled, but it can just as easily be a piece of plywood or whatever tools you have access to. And then there's threaded rods that connect the two bulkheads together, and that sled mounts to those threaded rods. On the 3D printed sled, it slides through them. You can do that really nicely. But if you're just using a plywood thread, historically I've used zip ties, or you can just glue on a section of tube. The section of tube that igniters come in works really well for some sizes of threaded rod, so you can get a bit creative there. It doesn't need to be the most rigid if you're just using a barometric altimeter, if you just have air pressure. So that'd be things like the Stratologger or Altus Metrum Easy Mini or an RRC2 or RRC3. Whereas if you're using an accelerometer-based altimeter, so that'd be something like a Blue Raven or a Fluctus, those need, I'm not as sure about the Fluctus, but those need a bit more rigidly mounted things because the accelerometer, if you have it wobbling around in there, that will throw off the accelerometer readings. On the right is a little bit different. You can see it's the same thing with the battery and then the altimeter above it, but there's all wired just to one bulkhead on the bottom, and that's because this is the nose cone that's just in the, or this is an avionics bay that's just in the nose cone of the rocket. So there's no dual deployment here. It's just single deployment. Exact same principle, but instead of having the two bulkheads on each side, there's just a bulkhead on the bottom. The last thing I'll mention here, shown on the slides, is on the leftmost slide. There's what's called a terminal block. This is used so that you don't have to have, you can have your avionics bay fully wired up the day before launch, everything fully enclosed, and then on the day of the launch, you can plug in your charges externally instead of having to take apart your avionics bay to plug in your charges. Ideally, you don't want to leave your charges plugged in for, a couple days. You want to leave those shorted out, in a safe container until you're at the launch site and ready to plug them in. So it saves you some time wrangling your avionics if you have those, buttoned up nicely the night before, and you can externally hook up your charges. Not a requirement. You can see the avionics bay in the middle. I don't have those, but when you have the room for them, they do make life a lot nicer. Next slide, please, Rob. Um, Another thing that goes on the fin can, but is not crucially important to the epoxying assembly. You typically won't epoxy on your rail buttons. You could, but generally you just screw them on. You need to have at least two of them. There's not a whole ton of advantage to having more than two. You can add more and it won't be a downside unless you misalign them. Um, I also use, if you go remember back from when we were cutting the fin slots, I use that angled piece of aluminum to draw a straight line up and down the airframe length, and I use that to locate two positions for my rail buttons. Um, Typically, if I have a small rocket and I have, say, quarter-inch wood centering rings, I'll just use a wood screw and have it go directly into the wooden centering ring, and that'll be more than enough to grab it. But on a heavier rocket or where there isn't a centering ring in the right spot, a great technique is something like as shown on the left. So there's a T-nut and then a chunk of plywood and then a machine screw. And you glue that chunk of plywood with a T-nut inside your airframe, and that's a much, much more solid connection. So it really sucks on competition day. It happens sometimes where a team doesn't have the most securely mounted rail buttons, and one of them will pull off right on when they're going to launch on the rail, and they have to, pull the whole rocket down, go find someone that has a rail button that they can get, some T-nut or something that they can use, and then glue it back in or whatever. So if you avoid that headache and make sure it's bulletproof, put something solid inside, like is shown on the left. All right, next slide, please, Rob. All right. Another item that's adjacent to rail button is just bolting in connections in general. Basically, there'll be sections of your rocket that you want to separate and sections of your rocket that you don't want to separate, or perhaps some sections of your rocket that you don't want to separate right away, but that you want to separate later in flight. So for all these, you'll use some sort of bolt to hold them together. And very careful, when I say bolt, I'm referring to both metal bolts and shear pins. So shear pins are a category as well. If you want something to be strong, like if you're doing a dual deployment, you don't want your main parachute to come out right away, but you want it to come out later in flight. So you'll put a bunch of shear pins on that section to make sure that when, if you do your ejection test on the ground, to make sure there's not enough, jerk there to separate that section. But when that black powder charge goes off, you'll do that testing and make sure that that charge is sufficient to shear those pins. And all shear pins are just nylon bolts. You can buy them from rocketry suppliers, or you can buy them from any industrial supplier. I buy mine from McMaster Carr, for example. There's also another category that a lot of people love, but I personally kind of despise, are these shown in the top right, these push to connect rivets. People that love them will say, oh, they're great. You don't need to use any screwdrivers or anything to take them in and put them out. Personally, I find I need to use two screwdrivers to take them out. I kind of go in there and wedge them out like that. So maybe you have more dexterity than I do, but I personally don't like using the nylon rivets. I find screwdrivers with just one screwdriver on a screw is much more convenient, as shown on the left side there. Um, Additional warning, if you're using a softer airframe material like cardboard, it's not a concern with fiberglass, but when you're using cardboard as your airframe material, you may need to reinforce your coupler and your airframe, but mostly your coupler. So you can see on the right here, this rocket was flown successfully, but on the inside, there's some damage to that screw hole from the violent ejection forces. So if I was to fly this rocket again, I would consider reinforcing that. That can be as simple as dripping in some CA glue and then sanding it flush and drilling it out again just to harden up the cardboard around there. Or you could do a bit more where you glue in something on the back end. I've used like a chunk of a tin can before, for example. Um, Soda can, I should clarify. A tin can might be a bit thick. So something to reinforce it, because over time, if you do that again and again, that will wear out and it won't be as rigid of a connection as you would like. So if you're using cardboard, that's my recommendation. All right, next slide, please, Rob. Another important aspect is motor retention. So high power motors will come with a thrust ring built in. You can see on the left on a snap ring motor, this is just an external snap ring, whereas on the top right, there's a 3D printed part that makes it just rest on that cardboard tube. However, so that prevents the motor from flying upwards through the rocket. However, you need something to prevent the motor from falling back out the rocket once it's done providing the thrust, and especially once the ejection charge goes off to pressurize that section. If you don't have anything holding the motor in place and that section gets pressurized, the motor will get kicked out the back instead of your parachute coming out the front. And then you'll have the motor falling ballistically and the rocket falling ballistically because the parachute didn't come out. So very, very bad day. Motor retention is very important. There's a couple of common styles. On the left is, and also on this rocket I have here, there's an Aeropack. So it's out of focus. Well, it shows it on the left there. It was called an Aeropack screw-on retainer. Aeropack is just a brand name. There's a bunch of different companies that make this style of screw-on retainer, and it's really convenient. It is a bit expensive though, and I've seen some people 3D print their own, and I've also done that as well. 3D printed works quite well, but perhaps not for larger motors. Like on the right side, on the bottom right, there's a 3-inch diameter motor. So a 3D printed motor retainer that might be a bit too much heat for some PLA or PETG plastic. So you want to move to the techniques on the right, where on the right we have what's called a mirror clip or a Z clip. These are just sold at hardware stores for mounting mirrors to walls, or they'll be sold by rocketry suppliers as Z clips. Very important to get the metal ones, not the plastic ones. But you can see exactly how they work on the top right. You just screw it into your centering ring and then they clamp down onto the motor in place. And you can see one or two of those per motor. Or on the bottom right, you see another style where it's very similar to the mirror clip in the way it works. If it's a flat plate that gets bolted down entirely with multiple screws. And this can take a bit more advanced manufacturing to make. I made this one on a CNC. So if you have access to that, that's wonderful. But if you don't, you can use something more simple and those work great too. All right, Rob, next slide, please. Um, and then unrelated to building, but still, important to note, and people often have questions about it, is painting and finishing. You want your rocket to look nice for the competition. So here's a few general tips on how to paint the rocket. Um, Select the right paint that has the right finish and stuff you're going for. Um, if you have cans of paint and primer, make sure that you have like paint and primer doesn't replace primer. It just works as primer is the way I like to think about it. So if you would typically do, one coat of primer and 2 coats of paint, you're doing 1 coat of primer and 2 coats of paint. They're just the same can. So you end up doing 3 coats of the same can is how I like to think about it. Um, and just like adhesives earlier, if you're putting something on a surface and you want it to stick to that surface, you have to surface prep the surface. Um, and as well, read the can of paint. And if it says it works well for plastics and metals, then it works well for plastics and metals. And fiberglass is effectively a plastic as far as that goes. But if it doesn't work for plastics, maybe find a different can of paint or so. And then surface prep, as before, mostly is just to get grease off the surface. You want to clean it off with isopropyl alcohol, acetone, something like that. Make sure that it's clean before you put the spray paint on it, and then do multiple light passes. It's better to do an incomplete coat and then to have more coats go on after it than to do one coat that gets full coverage, but you put on a bit too much and you get drips and runs in it. Unless you're going for the aesthetic of drips and runs, but usually I try to avoid that. So and then, kind of as before, you have to read. We were talking about reading the chemical compatibility as far as what it can be used on, but as also the dry and the recoat times are on each can. And those are just what you have to follow. So if it says to recoat, within 1 hour or after 24 hours, don't think that you can come back 12 hours later and that it'll work okay. Come back 30 minutes later and put on the next coat or something like that. So just check what's specifically on the can you're using and make sure you're using it at the right temperature too. If I was, to look outside right now, it's raining outside right now and it's, 45 degrees. So it might not be ideal painting conditions outside right now. Well, the rain would make a mess, but even the 45 degrees, the paint is not happy at those temperatures. It needs to be ideally a bit warmer. I think it says 70 degrees on the can. So, let's say 60 to 90 ideally degrees Fahrenheit. That's all on that. This is another brief note on composite reinforcement. We talked about this earlier with the laminating epoxy. This is something that I put at the end because it's not really required for any aspect of competition, but you might want to think about it for, some part that you need to be really strong, or if you want to build, your own from scratch tubing or whatever, this is the way to do it. So you take whether it's carbon fiber or fiberglass cloth, and then you wet it out with that laminating epoxy. It's a whole rabbit hole in and of itself. But if you're interested, just saying, letting you know that it is an option. I have two different examples here of what might be more commonly intro projects to composite reinforcement. On the left, I'm fiberglass reinforcing a cardboard tube. And you can tell I use blue dye in the fiber, I use clear fiberglass, but the dye in the epoxy is blue. So the tube came out a nice blue color. And you can use a sheet cloth for this, or you can also use sleeves. I buy my sleeves from a company called Solaire Composites, and those work wonderfully for reinforcing tubes if you're interested. Um, on the right, I have an example of what's called tip-to-tip fiberglassing, or in this case, carbon fiber, where the carbon fiber, you have the cloth goes directly from one fin tip all the way across the fin, across the center, across the airframe, and then off to the other tip. And that does a great job of not only making your fins stiffer and reinforcing them, but also reinforcing the fin connection to the airframe. So that drastically increases strength. And if there is some scenario where you can't do through the wall fins, for example, a minimum diameter rocket where the airframe is the motor mount, a tip to tip reinforcement can give you that additional strength that you're missing from the through the wall. It's not, one to one, but it does add strength that you're taking away by not having the through the wall. And on the right, I'm using, you can tell it's black checkerboard, that's carbon fiber. So the carbon fiber and fiberglass process are exactly the same. And neither is good for you, but carbon fiber is notably worse for you than fiberglass, especially when you're sanding it. When I'm mentoring teams and working with them on carbon fiber, what I remind them is carbon fiber dust is worse for you than asbestos as a kind of red flag. So if you're sanding carbon fiber, make sure you have good dust collection, or you're outside, make sure you have a good respirator. And the same applies for fiberglass, but carbon fiber is way, way worse. All right, next slide, please, Rob. Um, Another kind of not required thing, but it's a technology you might want to use, so I threw it here at the end, is 3D printing in rocketry. I personally love 3D printing in rocketry. I've, 3D printed all different components of rockets. It works great for some things, not so great for other things. So it's more of you have to know when to use it and have a bit of restraint rather than 3D print everything. It's the future. There are some things that it's wonderful for, better than anything else. Some things that it's absolutely horrible for. And it's going to be more expensive, heavier, weaker than just a cardboard tube, for example. So tubing, definitely don't want a 3D print in my opinion. A cardboard tube is super cheap and super strong and super light compared to a 3D print. But a thing like, a nose cone, that works great. Those are kind of hard to manufacture otherwise by more traditional means. Companies, put in a lot of money for the molding to make, blow molded nose cones, or money into filament winding for the fiberglass nose cones. But if you have a 3D printer, you can just 3D print your nose cone. Or if it's in focus, there we go. Here's a fiberglass nose cone that I made myself. And the way that I made this is I 3D printed the inner profile mold, and then I laid the fibers on top of that with the laminating epoxy we were talking about earlier. So it's still a part of my composites manufacturing process as well for making a nose cone. Another example is in the bottom left. And I kind of talked about this earlier as well, where I have a centering ring that has built-in alignment guides for those fins. I think this is a great technology. The centering rings aren't super required structurally because you have most of the thrust transferred through the fin tabs with your good internal fillets. So it's totally okay if they're a weaker material than the plywood. Um, but you can add extra features too, like these alignment guides for the fins, or there's also a hole in this, which is the hole for the motor retainer, or a hole to put the shot cord through, that kind of thing. In the top left, I have another great example of what 3D printing can be used for. It's a jig to make sure the fins are aligned on this rocket. So all sorts of alignment jigs for making sure your fins are straight, making sure the holes you're drilling are actually 90 degrees apart. Stuff like that, 3D printing is wonderful for. And then kind of a last note on the right here, I have a rocket that is basically entirely 3D printed. There's one part that's not 3D printed, and that's the cardboard tube, which is painted white there, but the entire fin section, the entire nose cone, everything 3D printed on that rocket on the right. So pretty cool. Next slide, please, Rob. So lastly, have a notes about some failure modes that can happen in flight and how to prevent those when you're building your rocket. Most common failure modes, I think it's 67% or 76%, I think. And that data might be out, or that data is outdated. It's almost 10 years old at this point. So I might have to find some new data and see if that's been updated. But when NAR did the report that I checked, they said 76% of failures were in flight recovery failures. It wasn't the motor failing, it wasn't the airframe failing under like aerodynamic loading. It was the parachute not coming out at the wrong time, stuff like that. So that's generally what you want to avoid is you want to make sure you get your parachute out at the correct time and fully inflated to avoid all those failures. Um, some examples of that is a recovery attachment point failure. On the bottom left here, you have an example of what every experienced rocketeer will tell you to avoid, which is one of those bent hook eye bolts. So you can see it just unbent under just a little bit of recovery forces. So it's really a lot better if you can get a welded or a forged eye bolt to prevent this one. Um, One thing that also can lead you to separating at the wrong time is what's called drag separation. On most rockets, this won't be a huge problem, but there's some configurations where if your fins are really thick, or if there's a lot more drag pulling on the back end of your rocket than there is pulling on the nose cone of your rocket, the drag, like once your motor burns out, will actually just pull the fin section off the back, and those will separate, your parachute will come out. And that happens when you're going at burnout the fastest you will ever go. And that tends to lead to problems like the next one, which is a zipper. In the top right, we have an example, it's colloquially called a zipper, and you can kind of see why, because as the shot cord pulls out at those high speeds, it'll rip back against the airframe and cut through it. And it makes this kind of zipper pattern. So that's why it's called a zipper. So this is caused by high speed deployment, and you fix it by not deploying at high speeds. There are also other things you can do to mitigate this if you're worried about it. You can use a chunk of like pool noodle or something where it hits your airframe, where your shot cord hits your airframe to reinforce it. You can also use what's called a zipperless design. That's all I'm going to say on that. If you have more questions about that, we can talk about that later. You can just Google the phrase, it'll be up there. But that involves basically moving your coupler around and prevent zippers by design effectively. Um, Other examples that are not as common, but can happen, especially as you're pushing things and flying on, higher thrust motors and flying higher and faster. Fin flutter. What this happens is think about just like, a flag blowing in the breeze. Your fin does that too, just at a much higher speed breeze. But if you're going, supersonic with your rocket, things will flutter still. So if your fins are really thin and you're like, really big and your velocity is really high, your fins will flutter. And on the right, I have some photos that my friend Max got, which are incredible, showing these fins fluttering right before they fail. So in the first two pictures, you can see the fins fluttering back and forth. They are not straight at all. And some of this is rolling shutter, but they do actually deform that much. They're just not deformed in those exact waves as shown. And that leads to a rather dramatic failure on the last picture there, when the fins just come right off because they've had enough. Um, so if you want to avoid that, you can use, you can calculate the flutter velocity of your exact fin geometry and your fin material. Generally speaking, you make your fins thicker or stiffer in general, whether that's thicker makes it stiffer, or just you can upgrade the material from fiberglass to carbon fiber, for example. The last one thing I'll talk about is motor fly through. This is a rare thing to occur, but is very, very scary when it does occur. So this is why I'm going to preach again to have good internal fillets, that your fin tabs are securely glued to your motor mount. If there's nothing gluing your motor mount to the rest of your rocket, your motor mount itself will just shear off and fly straight through the rocket. And Frank and I have seen that and seen enough of that for one lifetime. So let's try to avoid that. All right. I think that's the last slide. Probably the next slide. Yeah, that's the
Yeah.
last slide. So that's all the topics that I had lined up kind of as an overview. Um, Open
We'll
up to
just,
questions, or I guess we can mention these resources before I was going to wait until after questions if it came up during
oh,
questions, but I can go over these resources as well
well, I figured I'd
before we
just
open it
bring
up to
this up
questions.
while we're waiting for anyone to jump off of mute.
Okay, yeah. So jump off of mute or put your questions in the chat. For right now, I'll just go over these and feel free to put the questions in chat or jump off of mute. Here's some other resources that I would recommend, basically. There's a lot of great videos on YouTube. I would personally recommend a channel by a guy called John Coker. He's a wonderful resource to the hobby. He runs the website thrustcurve.org, if you're aware of that, and he's done a lot else for the hobby as well. But he has these specific videos that are called Certified Level 1 and Level 2 in Style, which go over kind of the basics of Level 1 and Level 2 high power flying, as well as some more advanced techniques. It's a really, really good overview. I would recommend watching them on 1.5 times speed, but maybe that's just me. And the other wonderful resource I would recommend is the Rocketry Forum, and then specifically this forum within it, this thread within it. it's in the high power thread called properly bonding composites and what your government doesn't want you to know, which is a bit of a tongue-in-cheek name, but really gets into the nitty-gritty and covers everything you need to know about properly doing bond prep and properly bonding composites and just any material in general. So yeah, those are the resources that I have outlined. Happy to, chat about rockets or answer any questions on any other topics I talked about today as well.
Anyone?
I have a question.
Yes.
Hi, my name's Madeline. I'm from Queens, and last year we had a motor retention problem where our motor ended up like going into our avionics bay. So I just want to clarify. The kit that we got this year came with those Z clips, which I'd never seen before. Usually we use a Aeropack retainer, and that's what we are planning to buy again this year. I just wanted to check if we go with an Aeropack retainer, we don't need to use the Z clips, right?
Sorry
That
about
is
that. I was
correct.
muted.
Yep.
Frank, go
So go
ahead.
ahead. Go ahead.
Okay, yeah, that as Frank said, that is correct. You do not
Okay.
you could say one or the other. I will kind of raise a bit of a flag there. If the motor flies through the rocket, that's not a problem with motor retention. So you
Okay.
might want to look elsewhere to diagnose that problem, whether that's the thrust ring on the motor itself failed, which is unlikely, or something else inside the rocket failed that led to that.
Okay.
The motor retention prevents the motor from falling back out, like the back side of the rocket, not from flying through the rocket.
Okay.
Um,
Good
there
to know.
The
is, go ahead, Frank.
the Aeropack retainer does stop the motor from going forward, of course, and backwards, as long as the motor mount rings and the centering rings are adhered to the centering rings properly, as Adrian mentioned.
Yep.
I don't remember that happened last year. Did that happen last year at the event?
Yeah, our rocket like went off the launch pad and it went like maybe 100 feet in the air, and then there was like a flash of light and none of our parachutes came out and it landed like face down sticking into the dirt.
Uh,
Almost
that
sounds like a motor failure.
yeah, that sounds more like a motor failure than a motor retention failure.
Oh,
Um,
it
yeah.
it was possible.
Yep. So if you do have a rocket that comes in ballistic, sometimes the built-in thrust ring on the motor can shear off when under those high loads of coming in ballistic. I won't think that's maybe not where to look for the cause of your problem, but that just happened after the failure. That was an effect of the failure rather than the cause of it. I'm in agreement with Frank, where that sounds like the motor itself failed. One thing to look in that specific case, it sounds like there was two different problems. The motor failed, obviously, and didn't give you enough impulse to get up to altitude. Um, but you should look into the deployment criteria of the altimeter that you are using can sometimes be that. For example, on my preferred altimeter, the Stratologger, if you don't get to 200 feet, the parachute will not deploy because it will not detect liftoff. So I had one of my good friends flew a rocket to 198 feet with a Stratologger on board, and the parachute did not come out because it
Oh
did
no.
not get to 200 feet. So it's if your motor underperforms a little bit, and yeah, Frank remembers that, yeah, that was Chandler's Black Lock Goblin or Wildman Goblin. Anyways, so important to check the exact criteria that you have to use. For one example, previously, there was a CRL competition that required basically the end result was that teams ended up being relatively low thrust to weight, and the minimum thrust to weight requirement in safety code is 3 to 1. And if you do the math on that, that actually only gives you 2 Gs of acceleration. And if your altimeter is looking for 3 Gs of acceleration to detect liftoff, which some Ravens do, you will not detect liftoff if you only pull 2.5 Gs of acceleration off the pad. So things to check in like that teams have previously been bitten for to make sure that you actually properly detect liftoff so that you get your parachutes out even when things do happen. I've had motors fail on me before and then the parachutes still successfully come out because I programmed the altimeters in such a way that they will. So that's another thing to check.
Okay. Um, Another question I had was when you 3D print your avionics sled, Do you reinforce it at all? Like, do you put like a layer of fiberglass over it or anything?
Nope, not in the
Okay.
slightest. The loads that the sled is under are is actually really easy to calculate. It's the weight of whatever electronics you're strapping to it. Say you have a 50-gram battery or whatever you're strapping to it, and you multiply that 50 grams of weight multiplied by the acceleration. So say the rocket's pulling 10 Gs, you can just hang a 500-gram test weight off of it, and if it holds that, it'll hold in flight. Um, if you want to go back, Rob, you can go back to the slide I had with the avionics bays on it. Let's see. Yeah, you can see typically when I do a 3D printed, it's basically reinforced, even though it's not required to be reinforced. It's basically entirely reinforced by those threaded rods running all the way through it.
Okay.
Um, so if you want to be super paranoid, 3D prints are weak in tension across layer lines, but really strong in compression. So you could clamp down on those threaded rods and hold the entire structure in compression. But I don't believe that that would be required for most designs, let's say.
Okay. Okay, that's all the questions that I had.
All right.
Thank
Thank you.
you.
Anyone else?
So I do have a quick question. So the kit that we have, so what we were gonna do with the motor mount, because like our motor mount kind of came with a, I keep forgetting how big the motor is, but it is definitely not a 54 millimeter. I'll have to find my notes to see how big it is, but it's way bigger than that. And what we were planning to do was just buy another tube with longer fins and new centering rings, but finding those parts were actually a little bit harder than anticipated. And I actually don't know if anybody is, if a lot of people are looking for those parts, but they sell out pretty quick. And the option that we were going with was to use my wife's really fancy laser engraver to cut out the parts we needed. But what we did find, or what was recommended to us by one of our mentors, was a motor mount adjustment tube. So basically, what we would be doing is uh, a motor mount inside the motor mount. And I sent an email, but I didn't hear a respond back about it.
I
But
I sent you one, Kenneth.
oh, it did. I must have went right back over the top of that. I'm
Okay,
sorry.
it was your question. I replied to your question that you inquired to Brittany,
Yeah, let me see
and you're inquiring about using the slim line.
the slim line. Yeah, sorry. I've gotten like 50 emails like every day for the past couple of days.
I know,
Must,
but yeah, I know your kit probably comes with a 75 millimeter motor tube.
yes, yes.
Stay with that and just use a an adapter. Either go with Aeropack or go with the Slimline. The Slimline works just as good. It's a little cheaper than the Aeropack. There's more parts in the Slimline, and I think I mentioned about you got to make sure you bring. There's a couple of small parts, retaining rings that you must have with that kit to make it operate properly.
Okay, yeah, I just seen that.
Okay.
Uh, yeah, yeah. Because the reason why I was going to ask is if that was an okay thing, because we were having trouble getting some of our parts ordered with through our
Yeah,
college.
just use the 75 motor mount that came with the kit because if you got to change it out, you got to change it out. It means you got to change out the fin to implement the through the wall fin connection
Yeah, because
on the tabs.
we ended up just ordering that. So I like it looks like I ordered it just a um. It looks like I ordered just like I think the day of because we had to do a bunch of reordering on some
Yep.
things.
Yep.
So looks like I have already ordered that by that time.
Okay. Well, do what you
So
have to do. Yeah.
Yep.
yeah, but that was going to be a lot cheaper and easier option for us. But I was just going to ask and see because it does have a so its retaining method is a is the retain is like just a little retaining ring. I'm trying to pull it up right now. I have
Yep.
Yep.
I'm not
So
in my shop. I'm not in my shop. I can't show you.
Yeah.
Yeah.
yeah,
Bring up my.
typically you'll need like if you want to think about it this way, you'll need to retain both the retainer within the rocket as well as retain the motor within the retainer. So often there'll be an adapter plate that's included that adapts the rocket's retainer to work with the adapter. One other option as well is if your motor is longer than the length of the adapter, you can put it all the way through the adapter and then wrap a couple wraps of masking tape along the front of the motor, and then it'll prevent it
Okay.
from sliding out the back. I will pause for 1 second. I will go grab an adapter and I'll show that in person here. Give me one moment.
Right.
Okay.
Yeah, it has another ring on it for the to strap around the motor. If it's a long motor, it has the adapter metal for the back part, and it has a round band that you screw on the top on the diameter of the motor to keep it centered in the motor tube.
Okay. Yeah. Yeah. But like, yeah, I was just making sure that that was an okay thing, but
Mhm.
because, um, yeah, because that was basically one of our,
Yeah, Kenneth, motor adapters like that are sort of standard to allow, rocketeers to adapt their rockets to the different motors. Because if
yeah.
you are undersized, you can't really upsize a motor, whereas you can always downgrade, to a smaller size. It's easier to do
Right.
that.
I mean, with 3D printing, you can upscale anything, but
Yes, but it's hard to upscale a rocket that you've already epoxied.
yeah, I know. But yeah, I was just making sure because I didn't see anything in the FNL handbook uh,
It's
about
hard
it.
to cover every possibility.
Yeah, it was more of just like a clarification on making sure that uh, that we weren't going to have
Is
something
that is
illegal.
that is that the slimline one?
Yes, I believe it was the slim line.
Frank is asking about the one that I'm showing on my
Yep.
web camera here, and
Uh,
this is actually a custom one that I made, myself. It's a chunk of shipping tube. Oh, what's going on here? I'm gonna assume it's still working. There's a chunk of shipping tube, and then I have two 3D printed centering rings here, and then one plywood centering ring here that this plywood actually transmits the force directly, whereas the 3D printed ones just hold it in place. Um,
okay.
and then here, if I was using this in a rocket, I would put a wrap of tape. So here's like the motor itself is goes through the top up here. I would put wraps of masking tape around here until it couldn't fall out the back anymore. And then I would have the motor retention on the rocket grab onto this plywood to hold it in place, and that would hold both the motor retainer, would hold onto the adapter, and then the tape would hold the motor within the adapter. So I would
Okay.
personally do it. There's all sorts of different ways to do it as well. You could have a separate motor retainer within your motor retainer. You could have Aeropack uses adapter plates, and I think the Slimline will come with one of those as well, but don't quote me on that.
Okay. Yeah, I just don't want to have you know, no
Well, when
motor.
you yeah when you show up at launch weekend, I usually have a battalion of stuff that Adrian has there. Also, I have handmade ones too, and I have the regular manufactured ones. We got to get you in the air, so we'll do our best.
Yeah, yeah, no, we're trying to get in the air as quick as possible as we can too.
Mhm.
So yeah, yeah, we're once those parts come in, because we had like multiple steps that we had to multiple steps and hoops we had to jump through since that government spending kind of went around, and
Do you have
so
a mentor?
yes, yeah, we got a mentor other than Dr. Woodblack. We have Stacy. I keep forgetting his last name. um I just texted him a little bit ago,
Right.
but
So yeah,
the
make sure you communicate with those mentors. They know everything about how to keep a motor secured inside of a rocket for sure.
yeah,
Was
I've been
Stacy
in.
Worley?
I'm sorry.
Was it Worley?
Yeah, I believe it was yeah, Mr. Worley, I believe.
It,
He
wait,
keeps he insists on me calling him Stacy, so I forgot his
Really?
last.
he's the one that we've been seeing in a few meetings, and we didn't know, we weren't
Yeah,
really sure which team he was associated with. So it took
it
us
was
a
like
moment.
ghosting us.
Yeah, yeah, he's the first time I met him was at our rocket build, our little rocket build group, our little group rocket build thing that we had in January. But yeah, I've been in contact with him, and he's been really helpful. He's been a lot of things that I feel like he he really makes things super simple. So
Good. That's what you
yeah,
need.
Very glad to
Yep.
hear it. Yep.
yeah, but yeah, he's I've been in contact with him, and he's been helping us out a lot with our rockets, with with everything. But yeah, that's pretty much all the questions I had. In case anybody else needed to ask one.
Ask away.
Not all at once.
Ah, there's some good questions so far. So
Mike, your team good?
Yeah, we'll be meeting again in a little over an hour, but so far so good.
Okay. Okay then. If there are no other questions, feel free to always reach out if you guys think of them, 5 minutes after we end. But otherwise, thank you guys. Feedback will be coming out from CDR very shortly. We just need an extra day or two just to finish up some processing from the judges. But otherwise, it'll all be coming out. Adrian, a huge thank you again for
happy to
helping
help.
us with this. We always love to have your help. And gives
Thank you.
us a fresh face for the students to look at. As opposed to Frank and myself all the time.
Might not be all that much to look at, but it's variety.
All right, then other than that, I hope you all have a wonderful evening. Hopefully the weather is cooperating. I know it's a little wet up here in Wisconsin today, but hopefully you guys are having better weather where you are.
Well, it's a tornado season here in
Ooh.
Oklahoma, so
Oof.
yeah, we're looking at high winds, and my truck likes to I have to turn my truck a little bit, like 15 to 20 degrees to the right while I'm driving. So
Oh, well, stay safe down there.
Yeah, at
oh
least we
yeah,
just have rain.
Yeah.
yeah, no, this is the exciting part of Oklahoma, and I missed it. California doesn't have all the fun weather.
All right then. Have a great evening, everyone.